It is Wednesday night. It is 7 p.m. It is time for Let's Make It. This week, we are still on our flying machines build. So we're going to talk about motors and a few things like that tonight. We're going to show you some of the different size motors that we have and talk about them a little bit, talk about some of the builds, and just, I think we're probably going to finish up this week with, in general, we may come back in a couple weeks, talk about different things, and as questions come along, we'll probably hop in here and answer questions as well. But this may be the last week. Next week, we're going to be probably moving into 3D printing for a week or so, just to kind of talk about that. We never talked about that on the show before, and I've been doing a lot of it. In fact, I've broken my printer more times than probably the average person because I print so much. And I fixed it. So, I mean, they're very easy to work on, and they're very fun to work on. They're a little slower than what I would like. I would like to be able to speed them up. I'd love to speed that stuff up, but they're still very interesting. And I've been making a lot of parts with 3D printers. So we're going to talk about the whole process, how a 3D printer actually works, and just the basics of it. We'll show you 3D printer. We'll show you how we print things, how we can draw things. We've been using Adobe Autodesk Inventor to do our drawings and everything, and we're getting better at it. Still not great at it, but better. And we'll talk about some of that, how we get things out of it into AutoCAD, for example. I'm starting to use it for more things than just 3D printing, so it's very interesting. I have the lower end version of it, so I can't do a lot of the advanced sheet metal type work, but I'd love to be able to go to that way because so many things I make are made out of sheet metal, and I'd love to be able to get that in there. It's just so expensive, and I haven't been able to justify spending the cost for it. So that's all coming up in next week. We're going to start on 3D printing. And this week, we have our first episode of the Electronics 101 segment as well. Now, when we started the show, you probably saw that our sponsor, Ziobi.com, is still with us and going great. In fact, they told me last week, I can remember they gave me some numbers around the sales and the numbers of people. And they were pretty impressed the fact that we had people we had actually go and check things out. So and buy some things as well. So I don't know what all was purchased, but they said they were impressed with the numbers so far. So and again, they're still adding things to the inventory. They pretty much wiped everything out and started from scratch because they had almost a little bit of everything in there before, and they're now really really focused. And the word they were trying to tell me was it's curated. So I tried to say that a couple weeks ago, and I couldn't remember the name or what they said about it. It's curated, so very specific things, and they are using our show as part of the guide of that. So we have some things we want to work with, and I'm actually going to bring up something today. I want to see if you guys are interested in looking at another CPU called a Riot board. So we'll talk about that in a little bit as well. But first, let's get onto our segment here on the motors and everything, and after that, we'll do our other segment on the Electronics 101, and then we'll come back and talk about some future things and ideas I need some opinions on. So without any further ado, here is the segment on motors and all the other stuff. Okay, in this segment, I want to do a little bit about motors and this will go for any kind of motor, for at least for an aircraft. I'm a little confused about some of the motors for cars, but in general, this is for quadcopters. Some of these same motors can be used for airplanes too. So, but basically, a motor there's brush and brushless. I'm only ever used the brushless ones, which come with 3 pins, and it's basically the different windings that are in the motor. And you see this one has three wires too, right there. And they come in different sizes. So you can see these are similarly sized. But let me just say, from personal experience, the quality is nowhere near equal. This motor, which I don't even know the manufacturer, it doesn't even say on who manufactured it, which came off of Amazon, was like $6. And it works fine. And actually, I'm going to recommend you do that for your first quad if you build one, because you're going to crash it a lot. And you don't want to put on more expensive motors till you get past the crashing part. So this motor was, like I said, about $6. This is 1,000 kV, which if you remember the video from before, 1,000 kV is 1,000 revolutions per volt per minute. So if you're using an 11.1 volt battery, it'd be about 11,100 revolutions per minute on that kind of battery. And this is a 980. And these are outrunners. So you see the outside spins, not the inside, which is how most of these motors work. The bottom part's fixed and screwed on, and then this whole outside piece spins because the coils are on the inside, and the batteries, the magnets that are are on the inside or on the outside ring spins. So this is built much better. I mean, if you can tell by looking at it, it's only 20 revolutions per minute slower, which if you remember if you watched the video from before, if you haven't, go watch it. It explains the numbers. That's not actually 20 is nothing, so it's not going to really make much difference. Now, as far as weight goes, I would say they're pretty equal. This may be a little bit more, but look how much better built this one is. I mean, it's machined, it's balanced, it's really nice. I mean, again, these are more expensive. These are closer to the $20 range, and this is from T-Motor. And these were some no-name brand off of Amazon. But this worked. As you're learning to fly, these are great because they're cheap. And this one, I don't know if you can tell, it doesn't turn because it crashed. So, let me see if I can try turning it. Let me find the labels so you can see. If I push hard enough, it'll turn, but it won't spin. But it's really tight. So that's what happens when you crash. So you don't want to go and ruin one of these expensive motors. So that's really, and then these are pretty good sized motors. And typically the lower the number you go, the bigger the motor gets because you got more windings in it and stuff like that. This is a smaller one I'm still working on. And let's see if you can compare the motors. You can see how much different the motors are in size there. And this is a 2300 kV motor. So the bigger number means smaller motor because that just means it spins faster. And it spins faster, it's less mass, and it takes smaller blades and stuff like that. That's what you can see right there. It's a difference in size. And these are, let's see where to get these from. Ready-made quads, maybe? Ready to Fly quads is where I got those from. And they're actually nice motors, so I'm hoping I don't crash it very, very much because they're not overly expensive. Actually, they're pretty cheap compared to these particular ones because they're so much smaller, I guess. But they're not as, cost less as what these are. I actually couldn't find anything like that I liked on Amazon to try to save. But I'm getting pretty good at flying quads. I don't think I'm going to crash this one. This one's actually designed for racing, so it may actually crash. Who knows? But it's the difference in the motors. So I just want to kind of show you some of the difference in the motors that are out there. And like I said, if you're building your own, start with the ones from Amazon because they are cheap, but you're eventually going to want to upgrade to the nicer ones like this because they just fly better. Everything flies better, and I'm not thinking going to hurt these if I crash either. It feels like it's built really well, but there is a cost difference in between these, and it adds up over time. So that's a quick one on the motors. Okay, so that pretty much covers what I want to cover, at least initially here, with things that fly. I guess what I'm going to say. I don't. Some people are upset because I said I don't mention tricopters, and yes, they're valid. There's plenty of tricopters around. I see them all the time on the internet. Quadcopters, hexacopters, octocopters, whatever. Anything that flies, a multi-rotor. Let's call it this way. Let's say a multi-rotor. That'd be safe, right? Because it's multi-rotor. So anyways, yeah, we may come back later on and cover some of this. I actually like to do a beginning to end build through one of these instead of just the little pieces here and there I'm taking pictures of that I've shown, but I haven't done that yet. So I do have some other airframes that I can build out, and I may start that here soon and make it a point to record, beginning to end through the process. Okay, so without going too much farther, let's go ahead and let's play our new segment that we're going to start every week. So let me give you a little bit of background on this if you haven't seen the show a few weeks back when I mentioned what was going on here. We've always talked about electronics and things like that, but we never really explained the basics of electronics. And there's so many times we get questions, and I just realized people don't understand electronics, and I've always made the assumption that if you're watching the show, you have some basic electronics, but that's not necessarily the case. You can learn how to program an Arduino and do basic things without even understanding how the electronics part of it's working. You look at a drawing and says, put this resistor here, between here and here, and you do it and it works, and you write code, yeah, we're all done. But you really don't understand what the resistor is even doing there, or how did it get its value, things like that. So what we want to do is start with basics. We're talking like really basic. So if you're new electronics, this next segment's going to be really boring to you. And you can probably just fast forward to the end of the segment. Of course, you're watching live, you can't fast forward, but the whole idea is every week, at least until we get a good base of electronic knowledge, we're going to do these little segments. And they're really short. It doesn't take real long to do them. And I think it's good for people that are just starting out. And if somebody has a question about something doesn't understand, I may send them to a segment and say, hey, look at this segment. And I may put segments up individually, eventually on YouTube as well. So that we could just say, hey, go check out this. It explains what Ohm's law is or things like that. So that's what this next segment is about. So but before anything, let's go and get started. Hello and welcome to the very first episode of Learning Electronics on Let's Make It. And we're going to start out very basic this week. And every week we're going to keep building on what we talk about. And as we go through this over the next couple of weeks, you will get some knowledge. And if you already know electronics, I'm sorry. We got a lot of requests about this before and some of the problems we've noticed is also people don't always understand some of the electronic things we do. So we figured we'd do a little Learning Electronics 101 type of course. That's what this is. We're going to start this week with the very basics, the wire. The very thing that allows electricity to move through from one point A to point B. And there's all kinds of different wires. We're just going to cover a little bit of the basics today. You see on this little image here, some solid core, some stranded, some twisted pair. So we got a bunch of different things in here. But basically there's two types of wire. You see the top there is stranded. You can see there's tiny little strands in there. And that is the flexible type of cable. A lot of the cable you use, the extension cords things like that, are using that kind of cable because when you have solid, which you see on the bottom, it doesn't bend real easy. The stranded allows it to bend. The problem is it can fray, and unless you tin the ends, and we'll go through all that stuff later. But when we talk about this through this course, we may talk about stranded or solid wire. And in addition to that, we also may talk about its size. So there is a American wire gauge, or AWG, as you'll see it labeled, and there's different sizes. So if you look at the one holding on the left there, that is 14 gauge. That or 12 is typically what you have in your house. And as you see, the thing is, as the numbers get smaller, the wires get bigger. And that is the way that it is. In fact, it goes, you see when it gets down to 1 AWG, then it starts going bigger, and basically you have a number / a number. So the typical wires we work with, probably in like our typical jumper wire, is probably 24, 26 gauge wires, much smaller than this right here. But I do encourage you to go out and look up AWG or American Wire Gauge on the internet, because you find lots of information out there about the sizes. You also see on here it mentions about how many amps each one can run, and that gets smaller and smaller as you get higher up in the numbers. So you got the 26 gauge wires, it's even down much smaller. Something to really keep in mind when you're trying to size the right cable for your project. And actually, here's a good example of a chart that gives you a 12-volt circuit and how long the cable is and how many amps as to what gauge wire you should be using. You can find these all over the internet as well. And then, so if you're trying to figure out what size circuit you need, you can pretty much Google it. Google pretty much knows everything, and they can recommend it as far as to what size cable you need. For most things electronics that we work with, 18 gauge is probably normally the most you would ever need, unless you're getting into more higher power things, speakers maybe, something like that as well. All right, so let's get down to some basics here. And we're going to talk about voltage, current, resistance, and power. These are all very important, and as we walk through here, you'll see. Voltage is often referred to as electrical pressure. So think of it kind of like the water pressure that's in your house, in your garden hose. But instead of moving water, it's moving electrons. So that's what voltage is. Think of it as water pressure. Current is defined as the number of electrons flowing at any one time past a particular point. So if we were looking back to the water hose or the water pipe, the larger the hose or the pipe is, the more gallons per minute of water that can move through that particular pipe. So think of the current as the size of the pipe. If to look at current as a measure of how many electrons are flowing per second. So that's we have water pressure, and we have water volume. So voltage and current.
Then we're going to talk about resistance, and it's exactly what it sounds like. It is resistance. It is the ability to restrict the current, or in simpler terms, reduce the flow of electrons. And this can be done using a resistor, most components do have some resistance in them as well. So as you add components, you have to make sure you look at the resistance that's in the component, because they typically add some resistance in the path. But if you purposely want to slow down the electrons, you use a resistor in the circuit. We're going to talk about that here in today's episode as well. And then last is power. So we know power as watts. If you look at your light bulb, your 60 watt light bulb, the power rating on that light bulb is 60. And it is basically the multiplication of the voltage and the current, and it just provides a measurement of the total amount of electrons over a period of time. So let's use this example back to water again. If you were filling your pool with a garden hose, and it was a small hose, even though it had high pressure, it would still take a long time to fill the pool. The pressure may shoot it across the pool, but the amount of water that can fit through that hose is only so much. So in the same way, if you had a fire hose, the fire company comes out, but they had no pressure, it would just trickle out. It would take a long time to fill up the pool. But if you get that same fire hose and put high pressure behind it, you can fill up the pool in no time at all. So you can compare power to the gallons per minute that you get out of a hose. So before we move on, let's look at voltage, current, and resistance and power, and the terms that we use day to day when we talk about these. Voltage is measured in volts, and it has the special code of V, which we're going to be using in some math equations here in a little bit. So remember, V is for volts. Current is measured in amps, which is I. I don't know, so I can't remember why I. Resistance is measured in ohms, and it's represented by the code R. And power is measured in watts, which is P. So in the following calculations, we refer to each of these items above by that symbol at the end. So just make sure you remember V voltage, I for current, R for resistance, and P for power or watts. So we're going to talk about Ohm's law. Ohm's law is the basic foundation for calculating electrical values. It says that power is equal to voltage times current. In the water example, it is equal to pressure times pipe size. So you will see it represented like this. Power is equal to voltage times current. Or sometimes you'll see it equal, say P equals VI. The two letters next to each other are assumed to be multiplied together. P in power, P is measured in watts. Okay, power is measured in watts. I look at that. It's confusing. And voltage and I are voltage is measured in volts. V is voltage, and I is measured in amps. So the current is measured in amps, the voltage is measured in volts, and the power is measured in watts. That's what we call them. We'll talk about the units of measure. So here are some examples using the formula. So you have 12 volts at 5 amps. That equals 60 watts. You can also have 120 volts at half an amp, or 0.5 amps, and that equals 60 watts. So they equal the same number of electrons that are flowing. It's just one has a lot more pressure than the other one does, so it just equals out like that. So we talked about this before, the size of something. So this formula is always true. So let's say you know the wattage and the voltage, but you don't know the amperage, but you want to get it. So what you would do in that case is you would divide 60 watts by 120 volts, because you know what the wattage is, and you 120 volts. And we know that if you take voltage times amperage, you get watts. So if you take watts and divide it by voltage, you get amps. What that equals is a half an amp, 0.5 amp, which is basically the same thing we did at top, 120 volts times 0.5 amps. We already knew the answer, but this just shows you the formula in the reverse order. So far, I've been using mostly whole numbers to represent calculations. In fact, I was basing them around a typical 60 watt light bulb. I don't know if you noticed that, but 120 volts, 60 watt light bulbs, it uses up a half an amp. That's good to know. I used it around something that we use every day. So small electronic projects typically are measured in milliamps, much, much smaller. And a milliamp is simply 1/1000th of an amp. So in the calculation of 60 watts divided by 120 volts, we got half an amp. But we could also say it's 500 milliamps instead of half an amp. They both are correct, because 500 milliamps is half of 1,000, and that 1,000 is 1,000 milliamps is a single amp. And if you look at some of your electronic chargers for your phone or your tablet or whatever, you will see just how little power they use compared to other things in your house, like the light bulb, for example. And this is a good way of practicing some math. Go find some of those, look at them, and it'll tell you on there what its output is, and you know it's 120 volts or whatever the voltage is. Well, actually, it's 5 volts or whatever you're charging it at, and you can figure out how many amps it's drawing, and you'll find out it's probably pretty small compared to what you're thinking it probably was. So go check out some different power cubes or back of a TV or whatever, and you can test out your Ohm's law knowledge. And one last note before we move on here: power has to be dissipated somehow. Sometimes it's dissipated as heat, like in a hot plate or an electric blanket, something like that. Sometimes it's dissipated as light, like an LED or a light bulb, anything that generates light like that. Sometimes it's dissipated as sound. Think of a speaker. You're sending out power to the speaker, and the speaker has a coil in it, and it's magnetically moving a piece of paper to make sound, and that's dissipating out the electricity. And sometimes it's also done in physical motion, which the speaker kind of does, but I'm thinking more in this case like a motor. So it's still a magnetic field similar to a speaker, and dissipates that out. And even though that you're going into a speaker, sometimes if you could feel the speaker or the motor, it feels warm, because even though it is moving and translating that power into physical motion, still has to dissipate some power, because it maybe can't use it all. It's not very efficient. In fact, if you overload a motor and it can't turn fast enough, it has to dissipate that power into the coils. That's why it gets so warm. So that's something to remember about a motor and overloading it. So I mentioned earlier about a resistor. So we're going to talk about resistors. A resistor basically lowers the current flow and voltage, and it does that by putting something in the way of the electricity. So inside the resistor, there is a material that does not let the electricity flow at its normal speed. And there's different types of material inside of all of these, and we're not going to really cover all the different types inside. Just know that it does cause resistance, and the current doesn't flow as easy. So, as I said, a resistor is exactly what its name suggests. It resists the flow of electrons, which limits the current. So there are many different formats of resistors. The ones on the previous page are the most obvious ones, and the ones that are used most in our small electronic projects on breadboards and stuff like that. They're very easy to work with. You bend the little pins, you stick them in, and they're really inexpensive as well. But they can be really small and surface mounted as well. I don't have any pictures of the surface mounts. I probably should have gotten some of those. But if you watch some of our other shows, you'll see on the boards that I make, I use a lot of surface mount resistors. And it's just a smaller format of the same thing. So each resistor has a number of values that are very important. And the first one is the amount of resistance that the resistor can provide. And it's expressed in ohms. I mentioned before about power is expressed in ohms. And power is expressed in watts. Resistance is expressed in ohms. And basically, the larger the resistance number, the more resistance that the resistor has. So if you have a 1K ohm resistor, it's going to have less resistance than a 5K ohm resistor. And the next number that we need to know about a resistor is the amount of power dissipation they can handle. Most common are an eighth or a quarter watt. Most electronic things we use are eighth or a quarter watt, because we're using such low voltage and stuff like that. But they can be as high as 2 watts. In fact, if you get above 2 watts or 3 watts, they actually call them power resistors, and they're designed for high power applications. So you've seen some of them around as well, but we're only going to cover the smaller ones in this course. And the last number is a tolerance, and this basically is how accurate the ohm rating is. So you can get them at 1% tolerance, 2% tolerance, 5% tolerance. So if you get a 100K resistor with 1% tolerance, it could be 99K or 101K. If you get it with 5% tolerance, it could be 95K or 105K. So just because all that is how accurate and what the tolerance level was when they tested the resistor. So we know what the numbers are, but how can you tell by looking at the resistor what the values are? And it's actually not difficult. Every resistor has a color code on it, and I'm sure you've seen these codes before, and you may or may not know what they were for. But they are basically done in 4 or 5 bands, and reading from left to right, the first digit is the most significant number, and the second digit is the second most significant digit. And then there's a multiplier. So, and then there's also a tolerance band around this side there. So if you look over to the right there, you'll see what value the first digit is, and if you look at the second digit, you'll see what value it is. And then if you look at the third color there, what is its multiplied amount. So you can kind of figure that out. And the last band there is tolerance, and there's only 2 colors for tolerance. Actually, there's 3. There's another band because there was 1% too. But you see down there, this particular one is a gold, which is 5% tolerance. So that's how you figure out the values. So what is the value of this resistor? I'll give you a couple more seconds to take a look at it. Okay, so we've not talked about the schematics or anything yet. In electronic drawings, we'll be a little ways down until we talk about some of that. But while we're on the subject of resistors, I do want to show you what the symbols are. And there's two basic symbols. I guess I consider these the American symbols. I typically only see the one on the left in most of the schematics. I occasionally will see the one on the right, and that may be actually the European version of it. I don't know, but the R1 is the value that I see a lot of. So 47,000 ohms is the same as a 47k ohms. Sometimes ohms is represented with the Greek omega symbol as well, which I couldn't stick one here. I couldn't find out where the fine looking thing was. So if you see it like in the little drawing right there, the 47k ohms, that is the symbol for an ohms. And before I forget, on the last page, the value of that resistor was 4.7k. So you get yellow is 4, violet is 7, and the multiplier of red is 100. So that's 4,700. Basically, you take and add 2 zeros to the end of the 47. So that's what that was. Sorry, I skipped by and didn't tell you that. The 47k kind of reminded me of that. All right. So we know that power has to be dissipated, and if the resistor is lowering the current, how is it dissipating it? And basically, it's what I said before. It generates heat. Most of the time, you don't feel it on resistors unless you're really overloading them. They're designed to be to run cool, so you probably won't even know it by touching it. But they do dissipate that as some kind of heat. So we do have to be careful when using resistors. So if you overload it, there is a great possibility of burning it out, it catching on fire, and you can also resistors do not last as long if you're keeping it up close to the top of the load value as well. So we're going to talk about that here right now. How you figure out what size resistor you need is you figure out what power it is, and we can do this one of 2 ways. The first is if we know our voltage and we know our resistance, is basically say the power is going to be equal to voltage squared divided by resistance. So in this example, we have 5 volts and we have a 1k resistor. So we take 5 volts times 2, which equals 10 volts. And then we divide by 1,000, and we come out basically with 0.025 watts. So we have basically 2.5 watts. So at this point, you could go up and you could get an 1/8 of a watt resistor and still be safe, or a 1/4 watt resistor would be just fine as well. So if we don't know that voltage, but we actually know what the current is, we can figure that out as well. So here's how we do that. We take, this is the same one. So here's where the results were. 5 times 2 divided by 1,000 equals 0.025. And as I said, calculated at 1/8 watt would be sufficient. Just make sure you double the wattage. And in this case, 0.025 watts would be 0.05. So that is much less than 1/8. So we can safely go to 1/8. Inductance less than double. More than double is 1/8 either. Okay, so let's build on the last example. And I said there's 2 ways we can do this. In the last example, we know what the voltage was. But let's say you only know what the current is. So here's the calculation to get the same power dissipation value. In this case, we take the current squared and we multiply it by the resistance instead of dividing it by resistance. Remember, we have Ohm's law here. So we're switching things around. So that's how we get the power, is to take the current squared and then multiply it by the resistance. So for example, if we know we have a 2.5 amps and we have a 10 ohm resistor, we take 2.5 times 2 and then take that times 10, which gets us 62.5 watts. Because 2.5 times 2 is 6.5 times 10 is 62.5 watts. So that's what we know our dissipation is going to be. All right, we have one more thing to cover this week in this episode, in this little short learning electronics episode here. And we want to cover is basically how you can combine resistors in either series or parallel to create the exact value needed for a task. So you can get resistors in many different values, but sometimes you don't have the exact value that you need. So what you can do is you can connect resistors in series to add up a total value. And that's basically when you put them in series and you say you have a 1K and a 2K, that comes out as being a 3K when you put them in series. So that's really simple. Let's go take a look at that. And right there you can see the example that you add up R1, R2, the whole way down however many you have in a row, and that equals your total resistance. And as I said, my example here was 4 1K ohm in series, and that equal a total of 4K ohms. Pretty easy to understand. However, if you put them in parallel, it makes it a lot more complicated. So each additional resistor added will basically half the resistance. So for example, you have a 10K resistor and you put another 10K resistor in parallel with that 10K resistor, you now have a 5K resistance value. So you see it cut that value in half. It doesn't make it 20 like you would think, or maybe 10 that we think it would stay at 10. It does not. It drops it in half. And if you have two more resistors, so you total of 4 10K resistors, you will actually have 2.5K ohms. So you see it keeps dropping down the more you add. So confused, I understand, and I always have to go figure this out every time I have to do this, because it's one of those things I don't do it enough to keep it in my head straight. But here's a real simple way of doing it if you have the same value. If you're trying to reach a particular value, here's what you can do as long as you all have the same values. It's a really quick way of doing it. Basically, take 1 and divide it by the resistance value. So in our case, we're talking about 10Ks. So that comes out to be 0.0001. And you multiply that number by the number of resistors. So let's say I have 5. So 5 times 0.001 is 0.005. And then I take 1 and divide it by that value to flip it back around again. And that equals 20K. So basically, I have 5 resistors, 5 10K resistors, and I get 20K out of them, the total. So you would think I would get 50, but I'm not. I'm getting 20K out of it. So let's take a look at it in a different way. This is actually the formula or the equation to generate it. And in the case that they're the same, it's easier just to multiply it. But if you have different sizes, this is the only way you can do it. You take 1 divided by the size of each resistor, and then you add all those up, and then you take 1 and divide it by that total that you added up. So it's doing basically the same thing as my multiply by 5, but I don't have 5 equal values. You have to add them up individually. So you can see that it gets very, very confusing and complicated. And people use both. I've seen people use both series and parallel resistors to accomplish their tasks. Because basically when you put the resistors in parallel, it allows you to put more power through them. So if you get a resistor that can't handle like your 0.25 watt resistor and you need to put a whole watt through it, you can put 4 of them in parallel to equal that. The problem is you're going to drop your value down. So you can either increase the resistance value of the resistor, or I've seen people take 4 parallels and put them in series with 4 parallels, so they basically get the same value back again. So it just you gotta make sure you calculate it out right so you don't burn anything up or hurt anything. Okay, that's it for this week. Next week we're going to take a look at capacitors, but a little bit of a homework project. This week, test your Ohm's law out. Like I said, go around, check out the different things that are sitting around your house that have power to them, and look at them and make sure that you understand how to calculate Ohm's law. And if it doesn't have the right value on it, figure it out. It's a good brain exercise to keep your brain working on Ohm's law, because Ohm's law is very important to know anytime you're working on electronics.
All right, our first segment is down. That wasn't too bad, was it? I know it's a little low level for some people, but other people, it's not low level. So I want to try to spread that knowledge around. Anyways, thank you, and we'll keep those kind of things coming. So back to the show. One of the things I've noticed is since we moved to Wednesdays, our chat room has been slightly light. And I know it's when you move a show, that's the kind of thing that happens until the groove gets kicked back in. And I have noticed that we have more live viewers, I think, now. And I'm hoping the 7 p.m. on Wednesday is the reason why we have that. Or are you still hanging out from the previous show? Who knows? Or are you early for the next show? Whatever it is, we're happy to have you here. But we do have a chat room. come in and chat live with us. Just go to tech-zen.tv, click on the live, and go to the chat room. We'd love to have you in the chat room with us. And along with that, well, I'll do the whole spiel about promotions later. I have a board that I've been playing with, but not enough that I'm overly comfortable with it, but I'd like to spend a lot more time with it, and it's called a Riot board. And it can run Linux or Android, and I'd like to spend a little more time playing with it on the show, but I'd like to know what everybody else's thoughts are on it. I don't want to go in a direction that you're totally not interested in. We've done a lot with Arduinos, and are we drying out the Arduino pool, or do we need to spend more time on Raspberry Pi, or do we go something different, like the Riot board? The Riot board is pretty darn cool. It can do a lot of things. What I have been struggling with, though, is getting things like SPI to work and things like that on it. And it's so new, I don't know if anybody really knows. I'm sure people know how to do it, but it's not like you can't go search the internet and say, hey, how do you use SPI in Linux on the Riot board, or how do you use it with Android? You just don't find the answers. So that may be something that's kind of fun to figure out, or it may be frustrating to people. I don't know. It's not an overly expensive board, and if people are interested in that kind of thing, do we go forward with it, or do we focus on the Raspberry Pi now for a little while? There is the BeagleBone. There's all kinds of different boards out there, and I just think we've gone a long way with the Arduino. And not that I want to abandon the Arduino, but I'm not sure where else, unless we have somebody comes back and says, hey, can you do this with the Arduino, that I could really go with it. So without your project ideas, but I can do the same similar things like we on the other platforms as I can on the Arduino, and address the differences, good things like that. So let me know. I kind of want your opinion. I kind of like to do a little bit of a Riot board type of thing, just because it's so much fun to play with. Or BeagleBone. I do BeagleBone too. I don't know BeagleBone very well. I'd love to learn it. I know Raspberry Pi fairly well, and I use it on a lot of things. And I'll go follow with that for sure if you want. No problem at all. So just kind of give me your ideas, and we'll try to get something spun up with that. Also want to know what you think about the ideas of a Hangout. Would you guys join a Hangout? Like after this show, if, let's see, maybe the show ends around 8. If we'd bring a Hangout, would you guys be interested in coming and joining and talking? That type of thing. I do that with a couple of my other shows, and sometimes it works, sometimes it doesn't. So it's really dependent upon you. Are you an introvert and don't like to talk to people? Or would you like to talk to people about electronics and get to know people like that? Just let me know. And we do Hangouts a lot, and I would not mind doing one for the show. It'd be perfectly fine. So it's totally up to you guys. I need direction from you on what you would like to do. So please let me know. Next week, we're into 3D printing. And again, check out our sponsor, Ziobi.com, and find some cool looking things out there too. I'm trying to convince them to do some stuff with quads and radios, but they're a little hesitant. So I don't know if it's going to happen or not. But it would be nice. Just a hint, Mr. Ziobi. So anyways, that is the show for this week. Tell your friends about us. We would love to pump up our YouTube. Love to pump it up. It's okay, but I mean, we do so much volume and off of Roku and our downloads, and I love the same representation on YouTube as I do on those two, because I think that we can get a lot of stuff out of YouTube, So tell your friends, go out to YouTube, click the like, subscribe. If you're not subscribed, please subscribe. That definitely lets us know that people are actually interested in seeing it on YouTube. At this point, we're only at a little over 1,000 or close to 2,000 maybe, and is it really somewhere we gotta focus our time on? Or should we not just do it there? Should we just keep it on downloads? I'd love to keep the YouTube going because our downloads are doing awesome. I think we can do the same thing on YouTube. I really do. So I need your help with that. But if you are not watching on YouTube, or you're watching us live, if you're watching us live, you're not in the chat room, unless you're one or two people, which I don't think you are. So come join us in the chat room. Go to tech-zen.tv and click on live, and you can watch us live right there, and you can join the chat room and chat with us as well. If you are watching this some other way but not automatic, what you can do, two things. You can sign up or subscribe in YouTube, which you'll get notified when we do new shows, or you can find us in any of the podcast directories. We're pretty much everywhere. If you have a Roku, we have a Roku app. You can watch us on your big screen TV. You can watch us live. You can watch the old shows. miss an episode, you can watch it back on the Roku. We'd love to have you do it that way as well. That is becoming very, very popular, and we love that. So yes, definitely spread the word. Tell your friends. You got friends, right? You have to have friends. Do they do electronics? Do you like electronics? Do you go to school with the people that do electronics? Maybe you're learning electronics in school. Spread the word. Tell everybody about us, whether it's on YouTube or it's through the podcast or the Roku or whatever. Just spread the word. That's how it helps us get found. That is our number one way of growing this show, and it's grown nicely. Even with our little hiatus there at the end of last year, we kept all that, seems like, and it's coming back up again. So definitely appreciate everybody's loyalty in that point of view as well. All right, well, everybody, we'll see you next Wednesday at 7 p.m.
For show notes for this show, contacts, and more, go to the techzen.tv website where you can get show notes for all of our shows. We love to hear from our viewers and listeners. We have an email, a Twitter, and a phone number where you can contact us for each show. For details, visit the techzen.tv website and get the show details. You can also make a video and upload it somewhere like YouTube or Vimeo and then just send us a link. You never know, you may see your video in a future show. You can get all of our shows delivered automatically to your favorite device by going to your favorite podcast website like iTunes and subscribing. Each of our shows also has a YouTube channel you can subscribe to get regular updates. Our shows are also available on most internet radio networks like Stitcher and TuneIn Radio. You can also watch and listen to our shows on Xbox, TiVo, and Roku. You can even find us on your Zune.